All right, welcome back to the Ethereum Protocol Fellowship study group. We are here on the 7th week, the development track today with Dragan from Reth, here to talk about the intricacies of an execution client. So, Mario, if you want to give a quick introduction for Dragan, and we will get started here.
Yeah, of course. First of all, thank you so much, Dragan, for coming. It's an honor to have you here because you really fit in our study group schedule. We had constants and execution layer specs last week in the first part of the development track, and starting from the abstract level of specs, we are now going to dive into the actual client this week, the execution client. And it's really great to have Dragan representing Reth here. Reth is relatively new, I believe, the youngest execution client at this point. Before, we had a similar dive from Matt into Get, not that like Get specific, but still Get is basically the oldest living client. And today we will have the comparison, the big architectural changes that Reth did, because Reth is very interesting, not just from the perspective of being new, written in Rust, but making many interesting choices and overhauling the whole execution layer design. So it's very interesting to learn from you. Dragan is creator of RV EVM, the Rust implementation of the EVM, and I believe the lead developer of Reth. Correct me if I'm wrong there. But one of the main maintainers of the Reth, which by the way recently became beta production ready, mostly, right? So congrats on that. It's really great, and you're here to present it. So yeah, the stage is yours. Please feel free to share your screen and dive into the Reth Codebase.
Hi, hello everybody. I am. Before the REVM and everything before that, I was part of Open Ethereum, and I worked on one of the Rust client that got deprecated. And after that, REVM got used by Foundry and everything, and Jojo's came and said, "Hey, let's build a client." And Jojo's leading the main effort around it, so I joined, helped a little bit, and yeah, I'm there and doing Reth and REVM and everything between. Let's start sharing screen. Yeah, I'm sharing full screen. Sorry about this. Let's start for just a second. Yeah. This quick presentation that Georgios did recently, it's good like introduction on the Reth, how it started, how basically where are we now, and the future endeavors that we want to make, and where we want to basically move it. Is introduced in December 2020. It was in that point of time, it was a few months of effort. I think we just finished our offsite where we finally peered over P2P. So that was very exciting. At that point of time, we only had like EVM that's used with Foundry, and it was very exciting times. First release of happened in June. Basically, this is where we synced the client, where we successfully synced from Genesis to the tip of the chain. And yeah, that's where we entered our alpha software. And just recently, like few weeks ago, we entered beta. Our few of our requirement for entering beta was some breaking changes on database that we had, and we started auditing both the Reth and our EVM so that we have more so that we are more sure that the client behaves as it should be. It helps a lot when you have audits done. But even without that, there is a big user base that already use Reth in production, and it was very nice to see that. Why Reth? Those a few points: client diversity, having fast, stable client that everybody can use for staking or just tinkering around it, or just using it for some hobby projects, or even use it in production to facilitate any provider infrastructure that they need. Talent resilience, more people knowing about core dev, knowing about core protocol. That's always good to see. Client scalability. We need client to build the high gas per second L2 world. We want to extend Reth to be usable by a lot of people, even L2s, L3s, whatever they come. And code extensibility, it should be easy to extend RPC, to extend EVM with new precompilers, everything around that. Fastest goals, L2 L1 Ethereum usage, fastest L2, and infrastructure for building EVM. We are very open for any contributor that want to basically jump into the code, check for good first issues, and just open PR. We're very proud for that because they have good and fast first response for any core contributors, and that's why we have these nice stats. They are basically growing. We are growing the stars and unique contributors. We are fast. For syncing Reth from the Genesis to the tip, it takes 50 hours, and it is around 2 terabytes of data. Historical sync breakdown. This was for 2023. We just recently with beta switched to the static files. I will talk about that a little bit later. But our archive node is around 2 terabytes, while our full node is around 1 terabyte. Async time in 2024 is 48, while in 2023 was 50. So even with increased state and increased, like new blocks came for a year, we are now a little bit faster than we were a year ago. For full node, this even more because we don't save all the data there. So 42 hours for full Genesis to the tip sync is very nice. There is the Aragon, and what we used from it. We have split how we sync the blocks. We have historical sync. Basically, the part of the Reth is optimized to sync historical blocks, and we can see that we can have 2, or depending on the block, this is millions of blocks. We can have 2 gigagas per second for historical sync because we optimize on that. And while on the live sync, where we include block by block and check the state truths for every block, it is a lot less. It's 100 to 200 megabytes per second, megagas per second. This is measured by Mega ETH Labs. We benchmark those stuff by Flood and by Creo, both very nice tools made by Paradigm. Yeah, we are currently transitioning. We transitioned to the beta and have support for the Cancun and everything around that. We are fuzzing the EVM currently, and we support OP stack. Snapshot syncs are done by the Merkle. You don't even need to sync from Genesis to the tip. You can just download the snapshot and just reuse it. We have good docs that's very nice to read. JSON RPC with all the traces that you need. Yeah, we get Reth in recently just entered Protocol Guild. That was very nice to see. In production, this one meme that was made. I'm running validator with Reth and Prism, run testnet, right? Testnet. So there are people running Reth and even as the validator. That's very nice to see. We target production to be production ready in May. So there are two audits currently in progress. Sigma Pride does the Reth, and REVM is done by Gaudo. He's first ETH bug bounty leaders on leaderboard. And there is three tracks: core development, performance. So there is few paths that we can be exploring, from GTVM to parallel EVM to we just parallelized our Merkle tree calculation that's currently merged. And kernel is allowing modification on the kernel code outside of the repo. So you don't need to clone it. You need to fork it and make changes. That can be very troublesome and time consuming. You can just use all these there and just extend it by RPC endpoint or new precompile. We shipped Cancun. We are on top of the Electro Prague. I'm basically working on EF currently. We are looking in vertical trees, account abstraction. There are a few APIs implemented as the part of the kernel or part of the node builder. Sorry. Yeah. Performance. This is paths that we investigate currently. Some of them are probably going to be implemented. At kernel is SDK for building bleeding edge EVM infrastructure. Basically, you can make pluggable components that plug in the current node and just extend it. Few ideas to merge a lot of project that needs to be run in the parallel into one binary that can be very nicely like run mainnet and everything is like there. These are few examples. I'll go over them slightly. This is examples of Reth kernel. And beyond everything, yeah. Multi-node rollups, multi-tenants node architecture. We'll see. It would be very nice to have like Reth node, mainnet, open mainnet, everything running on with one command. But this is more like mid to not immediate priority. Not immediate, yeah. I'm sure if you guys have any comments or anything you want to ask or anything you want to say, just write it and I will see to answer it. I will check chat from time to time. Mario, if you can ping me from...
Most of the time our chat happens in a Discord channel, which I can send you a link to if you want to join it. But Mario and I will triage most of the questions that happen in that channel and answer what we can, and then bring up any questions that seem relevant or pertinent for you to answer.
Okay, nice. That sounds great.
Great.
That was like, yeah, I want to do like quick introduction. These slides were very great about that. So after that, I know that this is expected to be more technical. So I would dive into the code and check components that are interested, that is different from the get architecture, and why they are different, and what the more differences that we have. So yeah, hope that is okay. Not RAM, but paradigm. Reth has a lot. Paradigm in general has a lot of projects that we work on. Reth is the client that we work on. Foundry is testing for the testing and everything around it. Alloy is they focus mostly on the Reth dependencies. Alloy gives us the primitives, big numbers, gives us RPC types, gives us everything around the like RLP coding, everything around that. So primitives are mostly found in the Alloy. There is REVM that's just EVM that have journaling. It has like it allows running transaction, whatever transaction that is. And our Reth is the guy that uses all of that, and the client and binary. Project is divided in the binaries and the crates. Binaries have just commands and basically encapsulating everything from the crates inside one crate. And inside there is a lot of crates that basically we wanted to make it as to be easy navigatable, and for every crate to be reusable by other parties. For example, everything around storage is in the side storage, and we have database, provider, codecs, everything that encapsulate saving or loading data from the database. These allow few use cases where you can use providers that are abstraction over the database, that have some utility function, get block, for example, and run that as the use just this library and run that as your as the standalone process that can read directly from the database. This is very nice use case because it gives you a lot more performant reads. You don't need to ping JSON RPC or IPC or everything around that. You can directly read from the database, from the disk. It was, yeah. Maybe it's better to start. I think these slides I made last year, but the few things have changed. But the main overlook is still the same. The Reth is driven by the engine. Engine is the main brain behind that drives every other component. Engine receives fork choice update from the consensus layer and checks if that block or hash that is received from the consensus layer is valid, or basically decides what to do with it. There is, as I said, Reth has two modes of the syncing. One is the historical sync that's done by the pipeline. Basically, pipeline executes, basically syncs in the stages. And when you sync in the stages, you can optimize those stages and allows you to be more optimized and basically faster. And when we are close to the tip of the chain, we switch to the blockchain tree. Blockchain tree is another way that we sync to basically near the tip, where state truth, validation, execution happen everything inside the memory. Only when the block gets canonicalized, it get basically moved to the database. Provider is abstraction over the database that allows some helper function so that we don't need to directly use key value data. Downloader, it's used by both the pipeline for its first two stages or by the engine if it needs to close the gap to the tip. It's used to download blocks and headers from the P2P. And basically from P2P, when we are close to the tip, we push those new transactions that we received to the transaction pool. And transaction pool basically is Ethereum's DDoS protection. It has a number of transactions ordered by the gas price that users want to pay. And Payload Builder basically takes n first transactions, build the new payload that's needed for the engine. A few more components are added, like snapshotting. Snapshotting is our way how static files, where we move some data directly to the different kind of database that is in the binary form. And additional component is here missing. It's pruner. It allows us to have full node. Basically, after the blockchain tree canonicalize the block, that block needs to wait for like additional 32 blocks, 64 blocks to get finalized. After it gets finalized, or I think we have some buffer 10K. But after it gets finalized, we know that it's not going to be reorg, or we can, if we are in the full node, we can remove some data. But yeah, those components missing, but this flow is still the same or similar that it was before. Let's jump into, yeah. I think the main difference here is in pipeline. I will go over it. Because the stages, how we download blocks, how we check the blocks, are what's the different from the get architecture. And I'll go for that inside the code. Not that. Reth. Creates RPC pipeline stages. Yeah, but before that, we take good care of adding a lot of documentation around, mostly in the code, so it's easier to modify and extend. So it would be good to check documentation first. Not that. Pipeline. No, that's stages. Yeah. Stage in general is very simple. It have its ID, it have execute, like, hey, I need to execute, you're the next for execution. Unbind is needed if some reorg happen, and we need to unbind that stage that basically can have side block or side data. And this is helper function to fetch it if it is ready or not. Where is the preload stages? Pipeline. Just a second. Okay, let's jump into the code. Maybe it's here. Yeah. The pipeline is basically consists of the multiple stages. Pipeline is used for some of the command line interface to basically, if you want to unbind just particular stage, or we want to execute just particular stage, it's used for the testing or used for the debugging or in development or anything where you just want to, like, for example, run just Merkle stage, drop those tables and just run it again. Here's a list of default setup where we have from the first to the last stage. First two stages, header stage and body stage, are basically network stages where they fetch in this stage headers, and here they fetch bodies. They fetch it by the bundle of the end bodies, and they need to wait for the P2P or nodes that we requested blocks to return the body or the header stage, so that we need to take care if the body or is not received, or we need to check if that's correct body that we received.
Dragan,
Yep.
We cannot see the stages. You're showing a different slide.
Oh, I wanted to jump into the code. Sorry.
Yeah, we see different browser window. Thanks.
Okay, I didn't know that. Let me hide. Let me stop sharing. I will share. Sorry, I jumped into share screen. Yeah, I wanted to check this. Can you see my?
No, we don't see now.
Share entire screen. Okay, I need to enable. I need to come back. I need to reopen the Chrome. Just a second.
Sure. Okay, so we have a quick intermission. Folks, meanwhile, feel free to ask any questions you had so far.
Mario, maybe you want to talk a little bit about what the difference is between a historical sync and a live sync or a snap sync sort of situation.
Yeah, I wanted to ask Dragan so he can give more detailed explanation, because like it might be more specific to the Reth code base in general. It would mean like that whether the full node is pulling the current data and using them to sync, or syncing from Genesis. There was some question about the live sync versus the historical sync, Dragan, but we can get into that later.
Yeah. Do you want
how is it?
to go? Yeah, it should be fine now. Just a second. I want to share my full screen, and I jumped into VC Code, and yeah. Do you see it now?
Perfect. Yes, perfect.
Yep.
Okay. Sorry about that. I thought we have same.
No problem.
Yeah. Do you want maybe to go over the questions, or do you want to go over them later?
We can cover the questions, some of the questions now. So the question was so we can read it properly.
What is the difference between historical sync and a live sync?
Historical sync is like syncing historical blocks, while live sync is syncing the blocks that come from the consensus layer. Those are the next block that's going to be proposed by consensus layer, while historical sync is syncing those blocks that are already proposed, already known, and already verified. So we have different kind of like assumptions here. For consensus layer, when we receive block for consensus layer, we receive just one block, or maybe multiple blocks, but they are mostly like near the tip, like the newest block. While for the historical sync, we already know what block needs to be re-executed. So we are executing everything again, and we are executing them from like genesis to the tip or the close to tip, depending on what tip do we have.
Yeah, so it's getting the fork choice data from consensus layer versus like fetching the execution historical data. And so yeah, what Reth does is like the stage sync, the different approach to historical sync, which is highly optimized, and that's what you were getting into, just not showing us. Just so you guys have the context. This is the one of the biggest differences in the Reth architecture, that it's using this stage sync, and it's very interesting. It's a different than what Git has. Yeah, and there was a question exactly about this. How is it different from Aragon and Aquila? And this is the stage sync. It's something that was pioneered by Aragon. So, like, if you can maybe summarize what are the other differences to Reth?
Difference from the Aragon and Aquila. Basically, what we introduced is recently are the static files. We are using our database, key value database, that here like B3 inside basically on the hard disk. We just use just binary files. And we put transactions, block, and receipts, basically immutable data that we know it's not going to be changed. We put it in our format in the binary files. And with that, we got like a lot smaller database and even faster sync time, for example.
That's interesting.
Yeah. Other than that, block sync it to the tip with the blockchain tree is everything is in the memory, so we don't have in temporary files and anything like that. So that allows us to not store junk inside the database and basically handle everything inside the memory, and that handling is just the pending data that's still not verified. So that's one of the differences.
Cool. That's very interesting because I thought at first that it's going to have very similar. Like I understand the performance, like go with some legacy get base versus Rust will be faster. But I was surprised that when I synced that it was actually smaller at the time, like half a terabyte smaller. Now it's maybe even more than the Aragon database. So that's yeah.
We did a lot of optimizations, like basically compressing the data. We have our custom encoding that encodes everything, and even few for example, init data and receipt data, we use some compression so that it's like shrinked a lot. The main difference between while this is even possible is while the pipeline sync, stage sync is valid, is we don't do Merkle verification on every block, while the other pass client get Open Ethereum, everything like past generation did it at every block. We do it only at the end. So we still verify that our state is valid and everything, state root is basically there, but we don't have that overhead to check into every block.
Right. Yeah, that's a lot of optimized computation there. Yeah, interesting. So we are getting back to the stage sync now, and maybe so go ahead, share your screen, and we can continue with that, and then we'll be back for more questions.
Share screen. Here it is.
Awesome.
Yeah, we're a big fan of the docs. So yeah, the pipeline has the default set of the stages, and those are used for initial sync, basically when the pipeline is running inside the Reth. This header stage and body stage are two stages that run separately. We first run headers, check the hashes, check basically the parent hash, if those match or not. After that, we basically download from P2P a little bit heavier bodies. We do sender recovery stage. Sender recovery can be expensive, so we do it here. For every transaction that we receive in body stage, we need to extract basically it's who sent it. After that, our biggest stage is our most time-consuming stage, execution stage. Here we do basically take the sender, transaction, and header and just execute it inside the REVM. Output of this is basically we check if the gas is same. We basically create receipts and we create the change sets. Change sets are the changes that happen between accounts in one block. So it's block level change sets. If we executive block have 3, 4 transaction, 100 transaction, we will take all those changes and make one hash map of that. After that, in the execution flow, this Merkle stage is skipped because it has its own use when it's unbinding. Unbinding, basic execution happen when you go from the top to the bottom, while unbind happens in different order from the place where you want to unbind, where you find some problems, to the top. Account hashing, account stage, basically in execution stage, we have just the plain state where key value for the plain state is just address and account information. That's balance, nonce, and code hash. While Merkle needs that hashed, and while it needs that hash, it matters because of the order. So we have. I will go to database next and show you what exactly that means, how the database layout is made. But we need to take the plain state and hash it and save it in the hashed account table. We do that same for the storage, and then we do Merkle stage. Merkle stage takes account, the storage, hashed account storages, and creates basically state root, and we verify that state root is correct for the block that we need. After that, we have this is helper stage. It allows us to do transaction lookup. After that, those two stages allows us to access any history data. Basically, execution stage created the change sets. Basically, the data that was previously there before the block get executed, while those two stages index those. Indexing is done so that it allows us for every block number that we want to get the account balance, for example, or account nonce. This allows us that ability. Same for the account, same for the storage, and just back. Same for the storage, similar thing is for account. And finish state, we just announce that engine can start getting new consensus layer from fork trust update from consensus layer. If we go inside execution stage, not there. Let's go this. Execution stage is the biggest one, so maybe it's better to go to sender recovery. set and recovery, has like some commit threshold. Idea how we want to optimize this is we want to have some bounds. How much data are we going to commit? How much basically RAM do you want to have? I think this is just amount of the transaction we want to commit. For example, we check for execution in the sender recovery. We check, we get the input that tells us, hey, we want to execute this stage from the block 1,000,000 to the block 2,000,000 or 1,500,000. We take the next block range with transaction. Basically, we take blocks in that range. If it's empty, the target is reached. And for everything around that, we do recover range. Yeah. For example, we want to be very optimized in this way. This is very CPU intensive because it's done recovery. We spawn multiple Tokyo tasks that does everything in the parallel, fetch the transaction that we need if this is in static file. And after that, if everything is okay, report the problems. If it's not, and we update the database table that has that transaction senders. Idea for this as example is to show that every stage does one thing, and every stage can optimize its parameters on the stuff that needs to be done. In study recovery, it's CPU intensive, so we use a lot of Tokyo tasks to parallelize that, and we want to be as we can optimize that a lot nicer. Execution stage is one of the biggest one and basically takes the longest time to execute. The reason for that is basically EVM it's CPU intensive and needs to execute 2 billion transactions. It gets input table from headers, canonical header terminal difficulty, basically all headers and blocks and transaction. It access plain account state and plain storage, and bytecodes are in separate table, and updates basically are plain state and account change sets. Unbind it basically unbinds the changes that it happened on the plain state, and change sets got discarded. Hashing storage. I'm not sure if there is questions around this, or should I go over to the database?
There's not any maybe specific questions around what you're talking about now, but there's some requests for maybe you to go through the process of building a block and using the state transition function in Reth. Maybe that fits here, maybe it fits later on in the presentation.
How to build the block. Okay, I will come to the payload builder.
Cool.
Okay, nice. Storage is interesting one. In storage, we have a codex that does, for the keys, it needs to be encoded, while for the values, it needs to be compressed. We still need to have that. We cannot compress integer and lose the greater than ability. Compact, this is for compression. For database, static files. Yeah. We have abstraction that allows us to abstract away the database. Currently, we just have MDBX, but the idea was to replace it or have ability to switch the databases. These these are trades, basic abstraction over very low level database access, where you have transaction, mutable transaction that gives you write access. Cursor is interesting one that allows you to iterate over the values in the database. This can be very faster way to fetch transactions or block or calculate Merkle root when needed, because accessing the values one after another is a lot faster than randomly seeking the values. This is true for the writes. So if you want to write an amount of data, it's a lot faster if you can sort them and write it in sorted order. DB basically is the low-level key-value database. It implements where it is benches. Yeah, tables are most interesting here. Basically, the data layout that we have inside the Reth table view. Here they are. Canonical headers allows us key to block number to the header hash. Timer difficulty is used for the proof of work. Currently not used. Header numbers. This is utility. Block hash to the block number. Headers. This is the table that have headers indexed by the block number. Block body indices. We have, what's interesting here, we have transactions that are indexed by transaction number to transaction. And block body indices is basically telling us for this block number, amount of what transaction number basically falls into this block. Block commerce, block withdrawals. This is for the proof of stake. This is for the side blocks that got included commerce, basically. Everything is table. This table is like indexed by the ordinary transaction number, that basically number of transaction and number of transactions that got executed. It's a lot easier to fetch one transaction if needed. Transaction hash number is inverse. If you want to fetch transaction by the hash, we get the transaction number. This index it stores the highest transaction number of this block. Basically, it's not every transaction number to the block, it's the highest just. This allows us to, from transaction number, to fetch the block number. Receipts are indexed by transaction number. Bytecodes are indexed by its hash. This is the plain state. Basic execution stage updates the plain state. The plain state has just for the account plain state, it has address and just account information. Account information is just this balance announced, while the storage has keys, basically account, subkey, or in this subkey is hash, basically key of that storage. Because I mentioned subkeys, MDBX allows to have tables, duplicate values inside tables. this allows us to have a little bit faster access to some values. In this case, we can have main key, address, and subkey basically to be hash. Account history is interesting, but first I want to talk about change sets. Account change sets, storage change sets. For every block number, we have account before the section, and subkey of that is address. So for every block, for every change account, we have its previous values. Change set for the table. For every block number and address, for address is account, we have storage key and previous storage value. These change sets are generated by the execution and used by the Merkle tree to, or any history tracing for RPC if you need. For Merkle tree, it's used for the incremental Merkle tree calculation, because when you calculate our first Merkle tree, other calculation of the Merkle tree should be incremental. And after we have those change sets, we are doing account history, basically for every, in this case, sharded key, for every address, and basically it contains, for every account, every block, it contains list of blocks where that account got changed. So if you want to find block account balance of the block 1 million, we are checking where that account got changed next. If this change is 1 million one block, then we will need to fetch the change set of that account. So account history and storage history allows us to index the change set and find the change that happened in the history. Hashed account, hash storage are used by the Merkle tree. Basically, they need to have, for the first calculation Merkle tree, they need to have sorted hashed accounts. There was idea to basically merge hashed accounts and plain accounts, plain basically state with hash state, so that we only have hash state. It would reduce the footprint in database for around 100 gigabytes. It shouldn't matter a lot for performance. You need still, if you want to fetch account, you still need to hash it. But for our measurements, for at least historical sync, main bottleneck execution sync is EVM, so would matter a lot. Account tree, storage tree are Merkle, Patricia, basically the nodes that are needed for calculation Merkle tree. Transaction sender, it allows you to fetch the address. It's used in execution and it's needed for the sender recovery. State checkpoints allows us to know where the stage stopped and what we need to do next. Prune checkpoints allows us to have to know until when we pruned our data. Basically, pruning, there is multiple parameters that can be set, but pruning mostly means that we remove change sets and indexes of those change sets. So it removes history data. So only the tip and can be fetched. And the last table is, of course, history. Do you have questions around this? Or was this too much? Can you share?
No specific questions around that currently.
Okay, cool.
Yeah, I guess going back to talking about checking verifications, this is kind of back a ways ago, but what sort of like drawbacks does not doing the Merkle verification checks for every block have?
Drawbacks are basically we don't have proof of the history. The get and Nethermine Open Ethereum basically you could at every point of time fetch the basically Merkle proof of every storage of account. This is removed. We only have Merkle proof of one point of time. So we need to be aware when we do reorg at the tip to unbind Merkle tree and update Merkle tree. Maybe one drawback could be increased complexity, but in general, Merkle tree and everything around that is very complex because it's at the end you get just one hash and every verification depends on that hash. It doesn't mean you don't have intermediate steps how to get that. Where is the step that you made mistake or not? But yeah,
Right.
you asked
Thanks.
about about verification. What kind of verification? Block verification or?
Yes. So Matt was explaining the get Codebase from the perspective of state transition function. So basically creating a new block by verifying transaction and including them into a block, calculating the header, and like in reality, this happens when you're asked to build a block, but like generally that's like the verification in get, and of course it's different in red. But if you could maybe guide us through the code base where this happens, where the also like some like caveats like where the EVM precompiles are, which is specific to Reth, and yeah.
Yeah, there's three places where we executed the section. One is inside the pipeline. This is inside the stage. All of them are similar but a little bit different. Mostly different how they handle output of the data. Where it is? Metrics, stages, source. A lot of checks on the block and the transaction level are encapsulated inside REVM. So a lot of heavy lifting is done by REVM. For example, here, start block. Here in the stages, we iterate over start block to the max block, depending on the range of the blocks that we want to execute. We fetch header, we fetch senders of that block. And here we execute the verify receipts. Basically, here we have our block and we have total difficulty that's needed for the proof of work, basically history execution. And this is the we want to encapsulate different, basically it's called processors. For example, to have Optimist processor, then to have Mainnet processor, and to have ability to switch them when needed. For example, this is the mainnet. Yeah, the main processor that we have. In here, it executes inner block. It initialized basically REVM with header. It applies beacon root contract call. Basically, there is system call that's done on the with Cancun that updates consensus layer hash, block hash, and here we execute transactions. Basically, this everything is done in processor. For every block, we take transaction, basically this iterator, check the gas limit for that block, and transact. This is function of REVM. Oh, we are still here. Yeah, we fill the transaction parameters. Check if we need to call in tracer, or that we are calling it inspector with REVM. We basically need to add handlers for that tracing. And here we do transact. Transact in general, we are now in REVM. It validates the data that we receive from the Reth. It checks initial transaction gas if we are okay. It checks transaction against the state. So here we just check the data that we receive. Here we fetch the account that of a transaction, of the sender of the transaction. And we start execution. Yeah. We are now in REVM still. It was recently refactored, so we have separation of the context and the logic. Context is the data, transactions, block, and precompiles, while the logic is handled inside the handlers, how it's called here, context and handlers. A handler contains the list of the functions that contain logic. So you can do anything around that. Idea is in the future to be able, even it's used even now, to register new handlers that will allow you like optimist level changes or optimist like logic to be implemented inside REVM. Something similar, it's done in on the scope of the Reth, but it's a little bit nicer now. I still need to do some refactoring in REVM. Where it is transact. Transact. Here we are. The first handler is loading accounts. After that is loading precompiles. For example, you can have handler that loads additional precompiles. We now deduct the caller with the maximum gas limit that it can potentially use. Idea is so that while the section is in the process, he cannot like send more balance than he have. A calculate gas limit depending on the set gas limit inside the section and deducting the initial gas spend that's depending on the how much zeros and ones do you have and what type of transaction and everything around that. Here we execute it. There is at least two types of execution, ordinary call to contract and creating new contract. When this is finished, we have, here's the main loop. A few months ago, we had like recursion call between the subcalls when the contract call and the additional contract. This is now changed to just simple loop. So it's run the loop, the main loop of the EVM. Here is down, where it just loops over the stack frames. And stack frame is, for example, one call or subcall of the subcall. And it trusts interpreter that checks the bytecode and executes it instructions. Let's go back. After execution is finished, we have some basically we need to handle when the last frame of the execution, last call or create returns, we need to handle some logic there. After that, we reimburse caller with the gas that's not spent. We reward the beneficiary that's basically sending minor reward. Minor reward is sent for the proof of work, while this is it's sent for the board proof of stake and proof of work. And we handle output here that returns error if happened, or returns the bytecode, the bytes that got returned. Yeah, that's mostly it from the REVM. Transact. Yeah. Now we are inside the Reth, still in the processor, executor section. When the section gets executed, we got some result outside of it. We check how much time elapsed, and we commit that state inside our database. So REVM, it basically doesn't commit anything if you don't want it. That is basically returns the state that got changed. After that, we communicate gas, create receipt, and that's it. If you go back, you execute inner. We check if the gas matches the gas used, and we check if we have post-execution state change. That is minor reward that was before in the proof of work. We check do we need to prune data or not, basically not merge it or not. Merge transaction and receipts, return receipts. And here we verify every receipt, save receipt if they're okay. So both the stages use execute and verify receipts, while the block builder use just execute, so it doesn't need to verify receipts while the execution is happening. This is in the stage. Yeah, stage is one place where REVM is used. Second place is inside the blockchain tree. Blockchain tree. Event state block canonical chain. This is for the blockchain tree, everything is done in the memory. So we have some pending state that's used wrap around the database. Chain, it's not extend. Canonical chain. Oh, it's not that. Here it is. Bundle state. No. Shareable. Fork. Insert, not insert, but fork. Forgot how it's called. Try and set it to sideblock. Yeah, here it is. Parent chain, where we append the block to the chain that is currently inside the chain. Here we called validate the execute. Validate the execute. We need now to have like the view on the database that you want to execute on, plus the pending state that we have inside the blockchain tree, and we wrap that inside some database trait, and we create executor, block execution, execute verify receipt. We already been there. Yeah, basically it use the processor again to verify everything, to execute everything. Because both the blockchain tree and the stages need have all the data, need to just verify if they are correct or not. And the third place is inside the node payload, Ethereum. We have multiple builders for optimism for Ethereum because it's a little bit different. I think that's it. Default Ethereum payload builder. We create the database. We create the payload what's needed. Pre-block beacon root contract call. Basically, this is the system call enabled inside Cancun. We get transaction for transaction pool here. Check if we have cumulative gas used more than the set gas limit of the block that you want to build. Is AIP if it is blob. Here we create just REVM and we use REVM to transact. It doesn't go through the processor, it uses EVM directly. If it is error, that means the same validation or some checks are not correct. If it is okay, then that state gets committed to the database. And this is done until we have enough gas to fill the block. Miner fee, execute transaction. Yeah. After that, we commit withdrawals, calculate receipt root, calculate logs bloom, everything that's needed for the header. Stay true, calculate transaction root. Here we calculate transaction basically root. Here we should calculate. Yeah. That's mostly it. Is there any questions around this? I'm not sure if I killed listeners.
They're still here with you.
Ooh, nice.
And there were some questions. I'm not sure if block building related. Yeah. There was discussion. There was a question following up on the one that we discussed before on skipping the Merkle verification. So whether this also applies to like storage balances, like how do we get accurate accounts for a particular block when you don't calculate the Merkle? So basically, yeah.
Yep. I'm not sure if I understood. Yep.
Yeah. So the Merkle optimization, whether it is it compared to other clients, whether there is a difference how you get those basically intermediate states and all the data for a particular block when you don't get it from calculating it from the Merkle data.
For the blobs or accounts. For the blobs, we don't have anything. That's mostly on the consensus layer. But in general, yeah, we check. Assumption is basically that we can make is for the history block that are blocked for the finalize, we need to check it only once. We don't need to check every previous state, because if we check just the present state or present state in the tip, we know that we have correct state. After that, we just incrementally check Merkle state, Merkle like root, and that's a lot faster algorithm.
Yeah, can you, okay, another question here is whether you can sum up what is the sender recovery in execution stage?
Basically, when the section is sent, or you only have like the payload and you have signature. From the signature, you are recovering the sender. Basically, who is the guy or girl who sent that section. So that can be very CPU intensive, and that's why we have separate stage for it. We even save that value inside the database, so it's faster to fetch it from the database than to recalculate it again inside the execution stage.
Okay, and we were discussing the database engine MDBX. Maybe if you can tell a bit about that, like what are the main differences with LevelDB or Pebble that is mostly used by other clients?
MDBX, basically we shrinked the scope of how we use it. Static files for the transactions and blocks and receipts are perfectly fine. Basically, binary files in like open the file, put the section and some indexing. It works very nice. For MDBX, it allows you to have like atomicity in atomic like fetches from the hard disk level. So it allows you to have ability to open new process and read the database in read-only mode. That's one of the use cases. It is B-tree like a database. It's fast on the reads, so it's more useful for the execution. So yeah, we're investigating like replacement for it. I don't think that this is something that we are going to stay long term, but for now it's working and it's basically doing the job that it needs to do. So we are open for new alternatives, but for now, yeah.
Yeah, interesting. Yeah, reading the documentation in Russian, right?
Yeah.
We have an English one as well. Okay, I don't see any more new questions. Oh, yeah, there was, whether you could point us, yeah, we have like last 10 minutes. Maybe if you could show us the engine API communication and how this block building is triggered by the payload, like, or where does this happen on the engine API?
Engine API is a little bit hidden because it is inside consensus. So it's creates consensus beacon engine. Let's see. Full block client, listeners, hooks. Yeah, beacon consensus engine. Here it is. This main structure that has a blockchain tree, that has engine sync controller, controls the pipeline. And a lot of, basically, it is quite complex because it needs to synchronize a lot of components from payload builder to the fork choice update to the blockchain tree to the pipeline. And it's like control hub of everything around that. It is implemented as the feature. Here it is. Fork choice update. On fork choice update. It should be in that kind. consistent state, assure canonical, update head, process, payload attributes. Yep, here it is. There is RPC part that calls this fork trace update, but I think this main entry point, work with latest, should be adhered to, yeah. Basically in here, we check if the pipeline is active. If it's active, we are not receiving. We are in the syncing process. We check if we have right hook on the database. That's more here. Make canonical is we tell the blockchain tree to make this block that we received as canonical, because fork trace update has just a hash. And if this has some problems or there is some, I don't know, state root is not calculated correctly or something like that, we need to go to like error handling or fail canonical fork trace update. Or if this is okay, we need to check outcome. If it is already canonical, because it is possible to have multiple consensus layer basically connected to one execution layer. So maybe they are sending the same fork trace update. If it is already canonical, if it is committed, that means that it is sent to the database. And yeah, assure consistent state. Yeah, in general, there is a lot of things happening here. On fork choice update, where is the main? Here it is. This is the main pool. Yeah, we implement future. Basically, it is the loop over the beacon consensus engine that acts like it pulls everything actions that need to happen. One of them is fork choice update. One of them is process sync event. And I think here, pull active, finalize on hook result. Yeah, here it is, here, yeah. If this fork choice update, if this new payload that is received from the consensus layer, if this new event that needs to be happening, there is configuration. I'm not sure even what's that. Yeah, maybe I'm not the best person to explore this. But yeah, if you want to dive deeper, it's in consensus beacon e-engine. It handles basically synchronization between the pipeline, blockchain tree, builder, and everything around that, even the pruner.
Okay.
Sorry
well,
that I don't have. Yeah,
that's right. It's all right. It's all good. Thank you very much. We had a question about the 3 parallel crate. Whether you can give us just an overview. We have last few minutes of the 3 parallel. Yeah.
What we noticed, we had algorithm that implemented 3 parallel. Basically, we have 3 and 3 parallel. They do the same thing, but in different ways. We have very optimized way to calculate Merkle root from the plain state, from the basically after we finish the pipeline. But what we noticed, that same calculation was not good enough for the tip, because for the tip, basically, we need the better way to do it is to do it calculation in the parallel. I don't know exactly the algorithm. It's not the thing that I worked on. So it was very new. Idea is to, I think, just make it in parallel. Yeah, don't have a lot to say here, to be honest.
Oh, that's right. Thank you so much.
Yep.
Just a quick overview. Yeah. Any other parts of the code you guys would like to ask about? Maybe. Otherwise, I would ask something a bit more general, maybe, and a bit further from the Reddit itself, because there are many people, trying to contribute to learning Rust. I'm wondering whether you have any suggestions, any recommendations, advice for people getting into Rust and learning this unforgivable language.
If you're starting Rust, the book is the main resource. Basically, it's official documentation. It's very nice. I think every Rust developer started from there. It's that good. If you already know Rust and want to contribute, good labels. We work on good first. There are a lot of them. Good first.
Is it with dash or
yeah
good first issue?
There is a lot of small tasks that can be done. Move with their scan types to alloy. It's like porting and just Matt created for 4 days ago. Matt is amazing.
Does Reth already supports the OTS namespace for AutoScan?
Yeah. I think, to be honest, I'm not following a lot. I moved myself to the REVM and I have a lot of stuff there.
Get it.
But we have AutoScan. I think we have AutoScan support.
That's awesome.
For example, there is phase out ethers dependency replaced with alloy provider, for example. Alloys provider are new rewrite of ethers. Replace byte smooth with vector. There's a lot of small tasks that can be done by anybody. We joke around that there was even one guy that made a script where he scanned the issues, and if he found good first issue, he would just grab it. And he made the script basically comment in the loop, and it was broken. And
it was trying to snipe the first good issues and spammed comments.
Yeah, exactly. But either way, there is a lot of good first issue that can be taken.
Yeah, awesome. Yeah, I'm very excited about this part of Reth, being so open to contributors, especially how do you see it from your side as a developer? Is it hard as a maintainer to get so many questions and just PRs which might be low quality or so? How are you handling it?
Go with the flow. Basically, me as the basically maintainer, I need to take care of my time, but I want to help people because you never know. From especially REVM, I know that my first user was Foundry, and basically I wanted to support all. Maybe it's different. They're high level users, but either way, you never know when somebody is going to go. You never know what happened in the space, because you never know if you help this guy for a little bit, he will stay here for years or build something on top of it. I had questions from in Gmail, hey, something is not working, and it was one Rust feature needs to be enabled, and it started working, and he built around library around REV and everything around that. I think the team that was behind Foundry and the same team that's now in the Reth is amazing, and they take care of that. Basically, our Telegram group is like very lively, and I think there is a lot of responses, a lot of questions, and we are there to support. That's why you build community in the end.
Yeah, awesome. Yeah, I really appreciate the openness and the community approach, and I understand it sometimes might be tough with all of the contributors coming in. Yeah, we don't have any more questions coming, so I think we can wrap up here. But thank you so much, Dragan. Yeah, I really appreciate it. It was really great insight. We learned a lot. Also, like, I have more to learn about the actual stage sync, because it's really nice to see it in the logs, right? Like, I'm doing this stage, executing transactions, I'm doing this stage, doing this. It's really nice to see how the client progresses, but it's different to actually dive into the code. So I'm learning a lot. Thank you so much, Dragan. Yeah. And yeah.
Thank you for calling me.
We sent you the invite to Discord. Feel free to join.
Yeah.
We have a bunch of people eager to learn there. So if you are, if you feel like answering some questions, you're always welcome.
Cool. I'll join it.
For the audience, for the study group folks, we will continue the week 7 on Wednesday with a research track focused on Verkle trees. We will have 3 or maybe even 4 speakers covering the Verkle tree topics in one session. So yeah, don't miss that on Wednesday. And next week we'll have Paul from Teku explaining the consensus layer client. So after Dragan's execution part, we will have the consensus as well. Yeah, awesome. Yeah, so we really appreciate it. We have great insight, Dragan, and we hope to see you around the study group.
I'm glad I helped.
Yeah, thanks so much.
Have a great day. Bye-bye.
Yep. Bye.
Bye, everyone.